Good morning, everybody. Hope you're all healthy and safe at home. So, we are moving on to the next portion of our section 9.13, surface integrals. So, in this section, what we'll be discussing is known terminology called as orientation. So we all know what is meant by orientation. It is some sort of it helps us to identify the direction, right? Okay, so you can have it is positive orientation, negative orientation, upward, downward, and so on. So without orientation, actually everything seems to be very meaningless. I mean, we must be oriented and we must know where we should reach and all those points that we have to keep in life, in our daily life also. So similarly, in case of surface integrals also, while dealing with surfaces, as I mentioned earlier, like we have positive orientation, negative orientation, upward, downward. So you can right now you can have a picture in your mind about the orientation of any surface and all. So in this lecture we shall begin with the concept of orientable surfaces, or surfaces which have particular orientations. So let's see the definition. A smooth surface is said to be oriented or orientable if there exists a continuous unit normal function at each point on the surface. Okay, that is, we can find a particular, if you see the figure that is depicted, if you can find any unit normal, we can find continuous unit normal function at each point. Okay, I hope the concept is clear. I mean, in this also you can see that if you see this particular surface, it has two sides, right? One, the upper portion and the lower portion. So we call this vector field of normal vector functions. That is, the vector field n of x, y, z is called as the orientation of the surface. Okay, so we say that a surface is oriented if we can find continuous unit normal at each point on the surface, and the set of all that normals, that is a vector field of those normals, will be called the orientation of the given surface. And as you can see in the figure, this particular surface S itself has one portion up, the other one is below this S below. So as the surface has two sides, we can have two types of orientation. That is, if one is n, the other would be minus n. So I hope the concept is clear. If the orientation is actually the vector field of all unit normals which is drawn on that particular surface. Now this slide depicts types of orientation. One is the outward orientation. So here the surfaces that we are having are basically spheres. So one is outward orientation, that is all unit normals are pointing outside of the surface, and the other is the inward orientation, that is all unit normals are pointing inwards, inside to that of the sphere. Similarly, we can have upward orientation and downward orientation. So in the first slide, in that particular surfaces, in all those type of surfaces, we can have the types of orientation as upward one and the downward orientation. So that is, I mean, like it's similar to n and minus n. So these are the types of orientable surfaces, or surfaces which have orientation. So the next one is an example of a non-orientable surface. You might be familiar with this terminology, MOBIUS strip. So it is the form of a MOBIUS strip is as follows. You can see the one which is in blue color. So the specialty of this strip is that if we if you consider any unit normal over here and move along the strip, then the when we come to the starting point again, the unit normal will be in the opposite side. So you can see this in the next figure clearly, that if we are starting from this particular point and if we are pointing unit normals in this way, when we move along this MOBIUS strip, what happens is when we reach back to the starting position, the unit normal will be in the opposite direction. So at a particular, for this type of surface, we cannot explain the orientation, because it is, we cannot say that it is outward or inward, because I mean, it depends upon the orientation of a surface, completely depends upon the unit normal. So if you take a particular unit normal itself, once we move along this surface, it comes to a different position. So we cannot say that its orientation is positive or negative, or outward or inward, anything we cannot mention. So Mobius strip is a well-known example of a non-orientable surface. So it is an example of many things. So it's a very important surface. So that is an example of a non-orientable surface. So as I have stated before, that the normal gives us the orientation of the surface. So this is just a reminder of what a normal is. We have done this before. So the unit normal for any smooth surface, which is given by, the surface is given by g of x, y, z is equal to 0. The unit normal is n is equal to grade g divided by modulus of grade of g. Now we know what is the value of grade of g, right? It is dou g by dou x I plus dou g by dou y j plus dou g by dou z k. Now if at all the surface that we are dealing is of the form z is equal to f of x y, okay, then what we do is we consider g of x y z to be z minus f of x y, or f of x y minus z. Okay, so that is something that you can keep in your mind while doing the problem section. So that's it for today's session. So we have discussed what is meant by orientation, and the relation of the unit normal with the orientation. So just keep all these things in mind. With this, we shall wind up today's lecture. Thank you. Stay home and stay safe.